Hello, everyone. So last time we were looking at solutions of first order differential equations. So in particular, we looked at y prime equals f of x with, let's say, y of x0 equals y0. If you remember, we said that a first order differential equation needs one initial condition. And then we saw that by FTC, the solution of this equation is given by the following equation. Y of x equals y of x equals integral x0 to x f of t dt plus y0, assuming that f is continuous. Because if f is continuous, this function will be differentiable, and derivative of this function will be f of x. It can also be shown that y of x0 will be integral x0 to x0 of some function, which is 0 plus y0. Okay, so let's look at one more example. Let's say, suppose a car drives. Suppose that a car drives at a speed e to power t half meter per second, where t is time in seconds. How far did the car get in? Did the car get in 2 seconds? Starting from t equals 0. Okay, what is the differential equation that we have here? So solution, our ODE can be written as, well, speed. Speed is given. Speed means derivative of x, the position function. So dx to dt, x prime equals dx to dt equals e to power t half. Please remember that rate of change is same as derivative. And in the case of position function, rate of change of position means speed, which means derivative. So this is given, and the initial condition, well, initial condition is not explicitly written, but it says how far did the car get in 2 seconds, which means we want to look at the x of 2 minus x of 0, because we want to know starting at t equals 0, how far it goes after t equals 0. So we want to look at x of 2 minus x of 0. So we can just leave x of 0 as x of 0, or we can just set x of 0 to be 0 and then find x of 2. So let's assume so we can say that with x of 0 equals 0. X of 0 equals 0. Again, the reason is that, you know, the origin is up to us, right? We can set origin to be the start. Wherever the object or the car starts moving, we can set the origin there, right? If we set the origin there at the location where this car starts moving, then x of 0, we can assume it's 0. So that's no big deal. We can assume x of 0 to be 0, or we can assume x of 0 to be any other number, or we can say x of 0 to we just leave it as x of 0 and just find x of 2 minus x of 0. So it's no big deal because ultimately we want to find x of 2 minus x of 0. So it doesn't matter what we set as x of 0. But of course, the easiest choice is that we can set x of 0 to be 0. Assume the origin is the location where the car starts moving. Okay, so now we can use our formula now to solve this equation. Remember the formula that we had here? Well, the formula that I wrote previously was with the assumption that x is the independent variable, y is the dependent variable. But right now, t is the independent variable, t or time is the independent variable, x is the dependent variable, or it's our function basically. So we can write that formula this way, that x of t equals integral t0 to t e to power s over 2 ds plus 0, x of 0, which is 0. Right, I'm using still using the same formula, just different letters I'm using. Instead of x, I'm using t, and instead of y, I'm using x. And instead of y 0, therefore we have to use x 0, right? So just the different letters we use, because remember I said that in physics, we use t and x. In mathematics, we usually use x and y. So no big deal, just the different names for our variable. And because I'm using t already here, because I've used t here, right? T0 to t. So I have to use a different letter here. I cannot use t again here. T is already used here. So use different letter. X is also used. Use different letter other than t and x, such as s. Okay, so now if we calculate this, we need the antiderivative of e to power s half. So we can use e to power s half itself, but e to power s half, if I differentiate it, is going to be 1/2 e to power s half. There is no 1/2 here. So if I multiply this with 2, then I'll get e to power s half, right? I need an antiderivative here, right? This is an antiderivative of this function, because when you differentiate it, e to power s half derivative is 1/2 e to power s half. But then if you multiply with 2, you get e to power s half. And then I need to calculate this between t0, which is 0 here, to t plus 0. So this is going to be 2 times e to power t half minus e to power 0. And this is 2 e to power t half minus 2. This is x of t. So then our next, we need x of 2. So x of 2 will be 2 times e to power 2 over 2 minus 2. This is 2e minus 2. So this is how far, the question was asking how far the car moves in 2 seconds. So it moves by 2e minus 2 in 2 seconds. All right, now let's look at the next example. So example, find the solution of y prime equals e to power minus x squared with y of 0 equals 1. Well, again, we can use our recipe. You know, we had a recipe for the solution of the equation y of x equals this function, and we have everything here again. So we can say that y of x equals integral x0 to x f of t dt plus y0. And then this is going to be integral 0 to x e to power minus t squared over 2. So e to power minus t squared dt plus y0. y0 is 1. And then you could try to find the antiderivative of e to power minus t squared. But from math 114, you know that e to power minus t squared has no antiderivative. So you saw in math 114 that e to power minus t squared has no antiderivatives. E to power minus t squared has no antiderivative. So you may wonder, okay, how can we use this in practice? Like, let's say if you want to, but we know that y of x equals this function, but how does that give us some information? Let's say if we want to find, for example, y of 2 or y of 1, let's say, how can we calculate y of 1 or y of 2? We know that y of 0 is 1. That's given in the question. We also know that y of x is integral 0 to x of this function plus 1, but we couldn't find an explicit formula. We couldn't find a closed form formula for y of x. So the question is, although we don't have any closed form formula for y of x because e to power minus t squared has no antiderivative, can we still use this formula somehow in order to calculate or at least estimate y of some number? So let's see how we can use this formula to calculate or at least estimate y at some specific points. So although we could not find a closed form formula for y of x above, we can still use this formula to estimate y of x for any x using Riemann sums. For example, let's estimate y of 1 using the formula above. So y of 1 is what? Y of 1 is equal to integral 0 to 1 e to power minus t squared dt plus 1, right? Y of x was integral 0 to x e to power minus t squared plus 1. So y of 1 is integral 0 to 1 e to power minus t squared plus 1. Well, how can we estimate this integral? So there is an integral that we don't have antiderivative for it. This integral here, we don't have antiderivative for it. But we can use Riemann sums to find an estimation for this integral. So if you remember from Math 114, we had different types of Riemann sums. We had left Riemann sums, mid Riemann sum, right Riemann sums. So usually mid Riemann sums lead to better results, if you remember, compared to left Riemann sums or right Riemann sums. So let's use mid Riemann sum with n equals 4. Remember that for any type of Riemann sum, whether left or right or mid, you also need to fix a value of n, which is the number of subintervals, and then try to find the Riemann sum. So mid Riemann sum, the notation for mid Riemann sum is MR, and if n is 4, we can say MR sub 4. So MR sub 4 will be delta x times f of x1 star plus f of x2 star plus f of x3 star plus f of x4 star. And delta x is b minus a over n, which is 1 minus 0 over 4, that's 1 over 4. And then see, this is basically our interval 0 to 1. And then this is 1 over 4, 1/2, 3 over 4. And then we have x1 star here. As we are using mid Riemann sum, our xi star would be the midpoint of each subinterval. See, I'm using 4 subintervals. This is my whole interval, 0 to 1. Then I divide it into 4 equal subintervals. And then inside each subinterval, I need to look at the midpoint inside each subinterval. Why? Because I'm using mid Riemann sum. So inside the first subinterval from 0 to 1 over 4, the midpoint is here, x1 star, that is 1 over 8. And then this is x2 star inside second subinterval in the midpoint of, at the midpoint of the second subinterval. And that's the midpoint of this going to be 3 over 8. And then here, midpoint of this. Midpoint of subinterval, you know how to calculate it, right? It's just the average of these 2 points. 1 over 2 plus 3 over 4 divided by 2. So that's 5 over 4 divided by 2 will be 5 over 8. And the last one here, x4 star, this is going to be 7 over 8. So MR4 will be, so y of 1 is almost equal to MR4. And MR4 we said is what? Is delta x, which is 1 over 4, times f of x1 star. F of x1 star is 1 over 8. F of 1 over 8 will be e to power minus 1 over 8 the whole squared plus e to power minus 3 over 8 the whole squared. E to power minus 5 over 8 the whole squared, and e to power minus 7 over 8 the whole squared. So that's 1 over 4 e to power minus 1 over 64 plus e to power minus 9 over 64, e to power minus 25 over 64, and e to power minus 49 over 64. Okay, this is an approximation for y of 1. See, although we could not find closed form because e to power minus t squared has no antiderivative, still we were able to at least find an estimation for y of 1. Similarly, you can find estimation for y of any number, y of 2, y of 3, y of 2.2. And if you want to improve your estimation, if you want more and more accurate estimation, then you can, of course, increase the value of n. Right now, we use n equals 4. If you use n equals, for example, 5, it will have better, you will have better estimation. If you use n equals 6, even better estimation, and so on. All right. So far we looked at the equations of the form y prime equals f of x, which was, of course, a simple example of first order differential equation. So far we looked at y prime equals f of x. Now let's look at y prime equals f of y. Equations of the form y prime equals f of y. So what will be the equation? So our ODE will be y prime equals dy to dx equals f of y. So if f of y is not 0, then we can say that if f of y is not 0, then we can say that dy over f of y equals dx, right? And then we can integrate both sides to find the solution. Okay, so this is the recipe, a simple recipe to solve equations of the form y prime equals f of y. Now let's look at a simple example of this case. Example, find the solution of y prime equals ky, where k bigger than 0 is a fixed constant. Okay, so here we have y prime equals dy to dx equals ky. Now we can consider two cases, because remember we said that we want to divide both sides by the right hand side, which is f of y, in this case is ky. Now it's important, if you want to divide by a number or by a function, it's important to first make sure that that function or that number is non-zero, because otherwise if it's 0, you cannot divide both sides by that number or function. So here I have ky. Now this function, well, k is of course is assumed to be positive, therefore non-zero. But what about y? Well, it is possible that y is 0. So that means I have to consider two cases. One case, if y is 0, in that case, I will not be allowed to divide both sides by y or ky. And second case, if y is not 0, then we can divide both sides by the right hand side, which is ky. Okay, so case 1, if y is equal to 0. So if y is 0, we cannot divide both sides by y, but still we have to figure out whether y equals 0 is a solution for this equation or it's not a solution for this equation. How can we verify whether a given function is a solution for a given differential equation or not? Well, we just need to substitute it back. And if the equation is satisfied, then it is a solution. If it's not satisfied, it's not a solution. I compared this last time with the simple case of algebraic equation. Let's say if you have x squared equals 4, and you want to know whether x equals 2 is a solution or not. We'll just substitute x equals 2 back into the equation. Well, 2x squared, then it will be 2 squared, which is 4, and right-hand side is 4. The equation will be satisfied. Therefore, x equals 2 is a solution. But let's say if you want to know whether x equals 3 is a solution or no, when you substitute x equals 3 back, 3 squared is 9, which is not 4, different than 4. Therefore, x equals 3 is not a solution. So here again, if y is 0, then we can say that then y prime will be 0, right? Derivative of a constant function is 0. See, y equals 0 means constant function 0. Because remember, we said that before, that the difference between algebraic equation and differential equation is that in algebraic equation, your unknown is a number. In a differential equation, your unknown is a function. So you may ask me, how come we are saying that y equals 0? This is a number, not a function. Well, then the answer is, when we say y equals 0, we mean as a function. As a function, which would mean constant function. Not as a number. As a function, if y is 0, then y prime will be 0, left-hand side will be 0. What about right-hand side? How much will be right-hand side? Also, right-hand side will be ky, which is k times 0, and that is also 0. So in this case, left-hand side and right-hand side, they are both 0. And therefore, this means that y equals 0 is a solution for this ODE. Now, case 2, if y is not equal to 0, it's if y is not a constant function 0, then we can divide both sides by y. So then divide both sides, let's say by ky, then we get dy over ky equals dx. Remember, dy to dx was ky, so dy over ky will be dx. And then we will have 1 over k ln absolute value y equals x plus c. All right, the recipe was telling us that we can first write it in this form, then integrate both sides to find the solution. So first we wrote it in this form, dy over ky equals dx. Now we can integrate both sides, then we get 1 over k ln absolute value y. Remember that antiderivative of 1 over y, or integral dy over y, is ln absolute value y. And then antiderivative of 1, or integral dx, is just x plus c. Well, you may tell me why we didn't include plus c in both sides. But we don't have to, because c is an arbitrary constant, right? So even if I include plus, let's say c1 here plus c2 here, then I can just take this c1 to the right-hand side and then c2 minus c1, right? See, if I write it this way, still I can write this one in the form x plus c2 minus c1, and then c2 minus c1, I can call it c. And again, I will have 1 over k ln absolute value y equals x plus c. Right, so that's why I don't have to include c in both sides, because c is an arbitrary constant. So it's enough if you include it only in one side. Because even if you include in both sides equivalently, you can write it, take both constants to one side and write it still in this form. All right. And then I can say that if I multiply both sides by k, ln absolute value y equals kx plus kc. And then absolute value y will be e to power kx plus kc, which I can write e to power kc times e to power kx. And therefore absolute value y will be equal to plus minus, y itself will be equal to plus minus e to power kc times e to power kx. Now e to power kc, if I call it d, then I will have plus minus d e to power kx. And here d equals e to power kc is a positive constant. Right? Exponentials are always positive. So e to power kc is always, if c is a constant, e to power kc will be a positive constant. So d is a positive constant, but there is plus minus d. So if I call this whole package plus minus d, let's call it f, for example. F e to power kx, where f is an arbitrary positive or negative constant, right? Because d was positive constant, arbitrary positive constant. F is plus or minus d. So f could be an arbitrary positive constant or arbitrary negative constant. So this was the final solution in case 2. But in case 1, we had a solution which was y equals 0. And y equals 0 corresponds to the case where f is 0. If f is 0, then the solution will be 0 because 0 times anything is 0. So I can say that combining, so final solution, combining cases 1 and 2 above, we can say that y is equal to f e to power kx, where f is an arbitrary constant. In case 1, f was 0 basically because the solution was 0. In case 2, f was either positive constant or negative constant. So overall, f is either 0 or positive constant or negative constant, which means an arbitrary constant. Because any arbitrary constant is of course either 0 or positive or negative. Okay, so let's look at the next example. Next example, find the solution of let's say y prime equals 5y with y of 0 equals 2. So we have done all, this is a special case of the previous example. We have done all the calculations already. So I can say that solution based on what we observed above. See, of course, if I give this question in the exam, you cannot say based on what we observed above. You have to repeat the calculation, repeat all the calculation we did in the previous example. Repeat it again for these special constants, k and initial constant. Okay, now the solution was y equals f e to power kx, and our k here is 5. So we can say f e to power 5x. And what about f? So to find f, y of 0, we know it's 2. And y of 0 will be f e to power 5 times 0, which is f times 1, and that's f. So that means f is 2. So the final answer will be y of x equals 2 e to power 5x. Okay. So that's the final answer. But again, if this was in the exam, you have to do all the calculation that we did in order to derive this equation. Do not just use the final answer and plug the values. Just repeat all the calculation. But you can start from case 2, because you can say that y of 0 is 2. That's given in the question. So y must be non-zero then, because if y is zero function, then it must be 0 at every point, and y of 0 cannot be 2. So you could start with the exam, you could start with case 2. You could say that instead of saying if y not 0, you could say that we know that y is not 0 function because y of 0 is 2. Then divide both sides by 5y because k was 5, and then do these calculations to derive the final answer, and the final answer will be this. Okay, now let's look at the next example. Example, find the solution of y prime equals y minus 1 times y plus 1 with y of 0 equals 3. Okay. So again, we have y prime equals some function of y, which matches the general form we just considered. Y prime equals f of y. We said that we have to divide both sides by the right hand side, but first we have to make sure that right hand side is non-zero. Can we say that right hand side is non-zero here? So first solution, first note that y minus 1 is not 0 and y plus 1 is not 0. Why? Since y of 0 is 3, so y cannot be constant function 1 or constant function minus 1. Y minus 1 will be 0 if y is constant function 1. Y plus 1 will be 0 if y is constant function minus 1. But y cannot be constant function 1 or constant function minus 1, because constant function 1 will be always 1. Constant function minus 1 will be always minus 1. But here y of 0 is 3. So y at some point is 3, which is neither 1 nor minus 1. So y cannot be always 1, cannot be always minus 1. So we can say that y cannot be constant function 1, cannot be constant function minus 1. So if y is minus 1 is not 0, y plus 1 not 0, then we can say that right-hand side, which is y minus 1 times y plus 1 will be non-zero. So we can divide both sides by this expression, which is y minus 1 times y plus 1. And then we get dy to dx cos y minus 1 times y plus 1. So then that gives dy over y minus 1 times y plus 1 equals dx. Okay, so it was important to include this step here before we divide both sides by this expression. And we could conclude that this is non-zero according to the initial condition. If this initial condition was not given to us, let's say if the question says find the solutions of this and no initial condition was given, then again, similar to previous example, you had to consider different cases. One case, if y is constant function 1, then you have to see whether that's a solution. One case, if y is constant function minus 1, is that a solution? And another case, if y is not constant function 1 and not constant function minus 1. So if the initial condition was not given, similar to the example we did above, then you had to consider different cases. Case 1, case 2, case 3. But here, because the initial condition was given and it's 3, we could use that and make sure that this factor is non-zero, this factor is non-zero as well. Therefore, the whole factor, the whole expression is non-zero. And therefore, we could divide both sides by that whole expression. So we got this, that in dy over y minus 1 times y plus 1 equals dx. So if we integrate both sides now integrate both sides. And then we get integral dy over y minus 1 times y plus 1 equals integral dx. Now this one I can write it, we can use partial fractions, right? Remember from math 114 that to calculate integral of this form, you can use partial fraction. I can write this one as 1 over y minus 1 minus 1 over y plus 1. Because this minus this will be, if you take common denominator, this will be common denominator. Then this will be 2 over this guy. So I have to multiply the whole thing by 1 over 2. And integral dx will be x plus c. Then I will have ln absolute value y minus 1 minus ln absolute value y plus 1. If I multiply both sides by 2, I'll get this guy is equal to 2x plus 2c. And then I can write this one as absolute value y minus 1 over y plus 1 equals 2x plus 2c. ln of this, right? ln a minus ln b is ln a over b. So that means absolute value y minus 1 over y plus 1 equals e to power 2x plus 2c. Again, e to power 2c, I can call it d. So then it will be d e to power 2x. That means y minus 1 over y plus 1 equals plus minus d e to power 2x. Again, plus minus d, I can call it f. So f e to power 2x. And then can cross multiply. Y minus 1 equals y plus 1 f e to power 2x. Then I'll have y minus 1 equals f y e to power 2x plus f e to power 2x. If I take all terms containing y into one side, y minus f y e to power 2x, and all the terms not containing y to the other side, so 1 plus f e to power 2x, and y 1 minus f e to power 2x, 1 plus f e to power 2x, then y will be 1 plus f e to power 2x divided by 1 minus f e to power 2x. And to find f, and here f is an arbitrary positive or negative constant, right? Because remember, f was plus minus d. F was plus minus d, see here. And d was an arbitrary positive constant because it's e to some power, and f is plus minus d, so f is either arbitrary positive or negative constant. And to find f, use y of 0. Y of 0 was how much? 3. So we can say that y of 0, we have y here as a function of x. So y of 0 will be how much? Just replace x with 0. Y of 0 will be 1 plus f over 1 minus f. That's going to be 3. So that means 1 plus f equals 3 minus 3f. And then that means 4f equals 2. F will be 2 over 4, which is 1/2. So final answer will be y equals 1 plus 1/2 e to power 2x divided by 1 minus 1/2 e to power 2x. So this is the final answer. And if you want to verify this solution, of course, you can differentiate this function, find y prime. See, this you can use quotient rule to find y prime. And then you can also find y minus 1 times y plus 1. Remember, y prime is supposed to be y minus 1 times y plus 1. So use quotient rule, find y prime. You can, of course, easily find y minus 1. This is your y. You can easily find y minus 1. You can also easily find y plus 1. Then calculate y prime, and also calculate y prime, and also calculate y minus 1 times y plus 1, and then compare them. They're supposed to be equal to each other. That's one way to verify your solution. But if the question in the exams does not ask you to verify, you don't have to. But if you just want to be confident that your solution is correct, then you can verify if you have extra time, or if, let's say, you're at home, you want to verify your solution. This is the way to verify. You can find y prime, find the derivative, find y minus 1 times y plus 1, then compare left-hand side, right-hand side. If they're equal, then that means your solution is correct. And also you can easily verify this condition as well. Y of 0 equals 3, because you have the formula for y. This is the formula for y. We can easily find y of 0. Y of 0 will be 1 plus 1/2 divided by 1 minus 1/2. That's 3/2 over 1/2, which is 3. So initial condition is extremely easy to verify, but you can also verify the differential equation if it's asked in the question to verify, or if it's not asking, but you just want to be sure that your solution is correct and you want to verify it. Okay, guys.